have Yifan Wang, who unfortunately couldn't make it here. He's joining us through Zoom. He will be talking about generalized spinning fields and renormalization group flows. So Yifan, please take it away.
All right, thanks for introduction. And I'd like to thank the organizers for putting together this wonderful conference and for the opportunity, for offering the opportunity for me to come here and give a talk. And I also am very sorry that I could not come here due to last minute family problems. And I also want to specifically thank Chris and Masaki for doing the T2 auto transformation on the schedule so that I can give the talk at the same time, 10:30 in New York, as opposed to UK as previously scheduled. So my talk will be based on recent works with my wonderful collaborators. So let me give a shout out to my collaborators. I'll be the talk will be mostly based on two works. One work is with Fedor Popov, who was a postdoc at NYU and now a postdoc at Stony Brook. Another paper that is to appear with my student Sasha at NYU, Zemo at Princeton, and also some of the content of the talk would involve previous works, also with another NYU postdoc, Himanshu, who has now moved on to industry. Okay, and I should also point out that Fedor and Zemo are on the job market this year, and they're truly outstanding. All right, so let me start with some broad motivations, and so I'll be brief because you probably have seen a lot of these motivation slides throughout the week, because that's the theme of the conference. So as we all know, one of the key results in the study of defects is the very important work from Jun Kondo in 1964 that really kicked off a lot of more recent developments in studying defects. And it really marked the important progress in theoretical physics at large. And since the 1960s, defects has been studied in various of its incarnations, and different kinds of defect physics has been studied for different applications in mind. In one particular context, a defect shows up as boundaries and impurities. This is related to the original setup that Kondo studied in the 1960s, but has been generalized to various settings, including to consider higher dimensions, also consider lattice versus quantum field theories. And in this context, there are various versions of defects, which are characterized by different kind of interactions on the defect row volume, as well as interaction that ties up defect degrees freedom with the bulk degrees freedom. And because of this non-trivial interaction between the defect and bulk degrees freedom, the defects give rise to actually very non-trivial probe for the phases of matter in the bulk. And this is especially important in the cases where local probes are insufficient to characterize phases of the bulk physics. And because also the interactions on the defect row volume, these defects also give rise to new kinds of universalities known as defect universality classes, which refine the usual notion of universality for bulk homogeneous systems. And another way where defect shows up in various contexts is when you think about defects naturally extending space. In these cases, the defects give rise to operators acting on the Hilbert space of the underlying quantum field theory. For example, if you're in the CFT, it's natural to quantize your theory on the cylinder, and you have a Hilbert space defined on the spatial sphere. And if in that context, the defect is represented by this object in the shaded region, they naturally act on the Hilbert space. And this is the context where the notion of generalized symmetry comes in naturally, where you restrict to cases where these operators are characterized by certain topological properties, which is a generalized notion that replaces the usual conservation property associated with symmetry charges. And these defects further have very interesting properties when they're topological, characterized by various splitting, consistency between splitting and joining of these defects, and these F symbols that are important data that characterize the underlying symmetry generated by the topological defects. And you probably have heard about it in this conference. Another context where defects as extended operators play an important role is to formalize the notion of entropy, such as entanglement entropy and Renyi entropy, as certain correlation functions in the underlying CFT involving codimension 2 twist operators. And furthermore, more recently, defects has also been realized as a way to characterize universality classes of what's known as weak measurement. And in the context of holography and also in string theory, defects are important because they give us a non-perturbative window to understand extended objects in string theory and also in more general quantum gravity theories. In that context, either from the string worldsheet perspective or from the ADS-CFT perspective, defects give us a way to very concretely define and classify such objects, okay, and give us a very useful tool to analyze the dynamics of such objects in gravity systematically. And throughout these explorations, there are a number of lessons we have drawn. One important lesson is that defects seems to provide a unifying perspective on various kinds of strong coupling phenomena in quantum field theory. And many questions about quantum field theory can be actually naturally formulated in terms of observables made out of these extended operators defects. And then the answers, once you have reformulated the questions in terms of defect observables, the answer to these questions about phases of matter can be tied to understanding the dynamics of the defects. For example, to understand what this observable look like at a large distance, and that's related to the notion of defect RG. And in this context, the general goal is to understand defect dynamics. And a concrete way to proceed is to following kind of three directions. One direction is to understand axiomatically the structural ingredients that goes into the defect dynamics, generalizing what we are familiar with in the case of local operators. For example, in this case, we want to understand whether there's a notion of operator product expansion that generalizes to extended operators such as defects. And the baby step towards that goal will be to understanding, the combined effects of, say, two defects. And that's the notion of fusion. And we also know that symmetry play an important role to understanding phases of matter. And in the case of, in the presence of defects, we want to understand how the symmetry principles are refined due to the defect insertion and how defects transform under those symmetries, and together with new kinds of anomalies that may arise in the presence of defect. And finally, there are also very important dynamical constraints for bulk RG that we're familiar with coming from RG monotonicity theorems. And then there should be generalization of those that correspond to defect RG, which should be explored. And these constraints are, of course, very useful and very powerful, but typically this only leads to carve out certain parameter space in the possible behavior for the defect observables. But as theorists, oftentimes we want to actually find solutions beyond just constraints, and this requires additional tools. And in this talk, as you'll see, this additional tool will come from this very heavy machinery known as functional analysis. To kick off the main part of the talk, let me start from a motivating question, which we'll address in this talk. This question can be understood as follows. So start from your usual quantum field theory. So that for simplicity, let's consider conformal field theory. And instead of the usual RG flow that we consider by turning on relevant operator throughout the bulk, let's consider instead turning on operator, scalar. For simplicity, let's talk about scalar operator O. But instead of turning on in entire space-time, but let's turn it on in the codimension 1 subspace-time. And the transverse direction is labeled by X_perp. As long as this operator has dimensions smaller than d-1, this coupling is relevant and triggers RG flow on this codimension 1 interface location. And the question is, under this RG, what is the infrared behavior as measured by observables, say, in the transverse directions? Okay, so there's a question about RG, namely the IR fate of this UV defect at the long distance. And this is what I refer to as generalized spinning defect, because such a deformation to the bulk action, in the case when the deformation is restricted to one dimension, is what was traditionally known as the pinning defect in the lattice literature studied by condensed matter people. And you can also think about this generalized pinning defect as simply a version of RG flow, but now concentrated on higher codimension subspace. And here in these pictures, we have been focused on the codimension 1 case. Before trying to answer this question, it's good to have an idea of what are the possibilities for such RG flow. So let me kind of list the logically possible outcomes of this RG. The first scenario is that you start from a trivial defect in infrared with no deformation turned on. So you could wonder whether in the UV there's a trivial defect. So you could wonder whether infrared becomes trivial again. And a slightly more interesting possibility is that in the infrared, maybe the defect is not entirely trivial, but topological. So in the sense that there are certain non-local observable that could be detected by the presence of this defect. And the third, which is the more interesting possibility, is that the defect is conformal, but not topological. As you'll see, just using the RG monotone, the version of RG monotone applies to defect RG flow. We can easily first rule out scenario 1 and 2, and later on we'll use tools from functional analysis to refine what happens in the scenario number 3. So let's start with the first theorem, theorem number 1. This is going to be coming from the RG monotone. So in this case, the monotonic function for this defect RG is going to be characterized by what's known as the defect free energy, which can be defined by having the spherical defect inserted in your spacetime, and you calculate the Pattern function in the presence of this defect insertion and normalize by the Pattern function without this insertion, and take the logarithm that defines the defect free energy. And more importantly, you should be taking the scheme independent piece of this free energy, and that's what I mean in the following. So for the purpose of this talk, we'll focus on defect RG, this kind of generalized pinning RG in dimension 2 and 3. I'll focus on the codimension 1 case. For that purpose, we'll only discuss these 2 versions of defect RG that's known as the G theorem in two dimension applies to pinning flow in that dimension, and the B theorem. So what the G theorem states is that the G function has to decrease monotonically under RG, and the G function associated with the trivial defect is equal to 1. And equivalently, if you take the logarithm, which is what actually shows up in the free energy, it's 0 in the UV and has to be negative in the infrared. Okay? And similarly, if we study such a pinning flow in 3 dimension, there's a notion of defect RG monotone given by the B anomaly. So this will be the coefficient of a logarithmic divergence in the defect free energy on S2. And again, the B theorem states that the B anomaly has to decrease monotonically under RG, and it has to be equal to 0 in the UV because it's a trivial defect. And this was studied in these papers. And why is it useful for the ruling out the scenario number 1 and 2 that we mentioned before, namely the defect become topological in the infrared? This is because the G function and also the B function, log G and B, they are all positive if they're all going to be non-negative if the defect were to be topological. And so the IR values of the log G and B constrained to be negative rule out the possibility of the defect being topological. And this you can think about as a protection of the defect under RG from screening. And when I say a defect is screened, it means that the one-pound function, the one-pound function in the presence of a defect is 0 except for identity operator. If there's at least one non-identity operator that has a non-trivial one-pound function with the defect is not screened. Okay. Any questions so far? Okay, so we have already ruled out the scenario number 1 and 2, and then we're left with the more interesting scenario, namely that the defect in infrared is conformal and not topological. And there are certain caveats, in which cases there are other exotic scenarios, such as the runaway flows. And that happens in very special settings, for example, when the bulk theory is free or have a moduli space of vacua. And in the examples we'll discuss in this talk, we'll suppress those, we'll not consider those examples, okay? All right, so just before we move on to refine scenario number 3 with this heavy machinery from functional analysis, let me just make a side comment about generalized pinning flows in more general codimensions. So throughout the talk, we'll focus on codimension 1, but many of the statements we made before also applies to higher codimension. And if you consider this kind of hard codimension RGs, you can easily construct lines and surfaces. And these kind of defects are really ubiquitous in conformal field theory. So if anyone asks you whether or not conformal defects is a It's just a thought. It's not a real thing. You can easily convince them by using examples such as this pinning flows. And this is thanks to this non-trivial RG monotone, and that generally protects the IR conformal, generally protect the IR behavior of such a pinning flow from being screened, and thus leads to non-trivial, non-topological conformal defects. And furthermore, in cases where we understand very well the landscape of conformal defects, such as the two-dimensional Ising CFT, where classification was given in this paper, the pinning defects are really ubiquitous in the sense that if you consider pinning flows, for the moment, generalizing the pinning flows by including also marginal deformations together with relevant deformation on the line, it actually populates the entire zoo of conformal defects in Ising CFT. And furthermore, these defects, for those of you who are familiar with the topological defects, these defects also has a notion of fusion that you can define after suitably regularizing divergence that arise in the coincident limit. But it has drastically different features compared to the topological fusion. For example, it has this non-dualizable feature, namely when you fuse these defects, it's worse than non-invertible in the sense that you don't even have an identity channel that shows up in the fusion. And furthermore, in general, the defect fusion is also not associative. Okay.
Yifan, can I ask a question?
Yeah, of course.
So when you're ruling out the topological case for the two-dimensional spinning field, are you using about quantum dimensions of topological surfaces?
No, so you remember that uses the monotonicity B theorem. And the B theorem is the conformal anomaly, and it's always just 0 for topological defects. So we are in the easy case.
Okay.
So what you're asking is a good question. So I use the fact that in one dimension, so in two-dimensional pinning flows, I use the fact that G function is going to be equal to 1 or greater than 1 if the defect is topological. So log G is always non-negative. That's what I said. And then there's a similar story if you study pinning flows in 4 dimensions, codimension pinning flows in 4 dimensions. In those cases, you can rule out the defect in topology in the infrared. But then in that case, you have to study quantum dimensions of topological, interface operator that with 3-dimensional extent.
Thank you.
Okay. And then there's like a usual sign, like this monotonic free energy, the alternating signs when you jump dimension by 2. So that's something you have to be careful if you are thinking about, for example, putting Chern-Simons on the 3-dimensional topological defect and how that changes the quantum dimension. This is the thing you should keep in mind. Okay. Thanks for the question. All right. So this strong kind of dynamical consequence I was mentioning coming from functional analysis leads to the theorem number 2. What it states is that if you follow this defect RG triggered by relevant operator on the codimension 1 space, something very drastic happened in the infrared. It actually factorized the space-time into 2 halves. What does that mean? This means that the interface infrared can be represented as a direct sum over factorized products of boundary conditions for the left-hand side and right-hand side, labeled as B nu over here. And locality require this thought of as states to be generalization of what's known as Carty states in 1+1 dimensions. And in terms of equations, what this factorization is telling us is that if we study in the infrared correlation functions of operators inserted on the left, represented by OR over here, and operators inserted on the right, represented by OR over here, if we look in the infrared, meaning that this cluster of operators are going to be far away compared to, in the transverse direction relative to the interface insertion, then this correlation function, or equivalent in the infrared, would need to take this factorized form where there's possibly a sum that keep track of this direct sum structure in the factorization, in the case with multiple factorization channels. And the particular consequence of the Ball formula is that in the case of looking at energy, stress tensor correlator across the interface from the left and from the right, because stress tensor one-point function in the presence of a conformal boundary just vanishes, the Ball equation implies that stress tensor two-point function across the interface is equal to 0. Okay? This is very interesting because what this means is that there's no energy transmission across this interface. Okay? This is the usual characterization of a factorizing interface. And it's also a characterization of what's known as an energy shield. So upshot here is that the pinning field interface provides a way to construct the energy shield by just performing a local deformation in your quantum field theory. And to give I will not have time to go through the proof of this theorem, but let me present some rough idea of how this argument comes about. So the rough idea is to think about the spinning field operator as a defect, which I define as dH, depending on the insertion of this operator O. And H is the coupling, also known as the pinning field. And O hat is given by, sorry, there's a coordinate missing, is given by the integral of the deforming operator on the codimension 1 slice of your space-time. And the rough idea is that this pinning defect operator, when the operator is real, behaves as a density operator. When you think about this operator inserted in the spatial slice, it behaves as a density operator acting on the CFD Hilbert space. And because this coupling constant H has positive mass dimension, if you're looking at this defect, its property in the infrared, this density operator will be dominated by the maximal eigenvalue of this operator O hat acting on the Hilbert space. And one can show that the maximal eigenvalue is achieved for special combination of states in the Hilbert space, and this special combination precisely align with Ishibashi states that has these additional symmetries, namely they're preserved by this d-1 dimensional conformal symmetry. And of course, there are many subtleties that go into this argument because this operator O hat is not really bound; it's unbounded, and furthermore, it without regularization it's not even well defined on O hat. It does not map normalizable states. Sorry, it's not even well defined on the Hilbert space because it does not map normalizable states in the Hilbert space on SD-1 to normalizable states, except for except for measure 0 subset. So to make precise argument, it requires carefully using the spectral theory of unbounded operators, and that's the main contribution we gave in this paper. Okay, for the rest of the talk, we'll just take this theorem as given, and we'll explore the consequences. And before we look at examples, let me also mention constraints coming from symmetries that further refine the fate of the defect under a pinning flow. And this arises when you consider this pinning flow operator O that plays nice with topological defects in your theory, namely commutes with topological defects that generalize certain global generate some generalized global symmetries in the CFT. In those cases, the symmetry properties, for example, for zero-form symmetries acting on the defects can be captured by fusion between the topological defect and this and the defect that we're interested in. And because the operator that triggers the flow commutes with these topological defects, the fusion property in the UV, which is very trivial because this is just a transparent interface, will persist to the infrared. Okay, and as you'll see, this kind of fusion properties will predict the degeneracies in the factorization channel, and what kind of boundary condition that will show up in the factorization channel is tied to symmetry properties associated with operator O, and what kind of symmetry are present in the bulk theory. And in the cases where there's no symmetry preserved by the pinning flow, in this case, we expect a unique factorization channel, just like in the case of bulk RG flow. In the cases where no symmetry is preserved, we expect a trivially gapped ground state. In the cases where there's a finite symmetry that's preserved by the pinning defect, there could be symmetry enhancement. There could be symmetry enforced degeneracies in the factorization channels. In other words, some notion of symmetry breaking on the defect, as we will see. And in the more interesting case where there are actually continuous symmetry, global symmetry that's preserved by the defect RG, then in these cases, there could be actually emergent ghost stones at the interface. Again, we'll see these examples. For example, in that context, the infrared of this pinning defect is not strictly of the direct sum structure, and that's the reason I put like a apostrophe over here. Actually, could involve certain smearing over the zero mode of ghost stones that emerges on the location of interface. And even more interestingly, there could be even more exotic gapless modes that arise in interface under such a simple higher codimension RG flow. And for example, as we'll see examples, this is work in progress, that there could be emergent chirofermions that arises from such a pinning flow. And this will arise in the Grosnevu-Yukawa CFT. So let me, before discussing the concrete examples, let me give a summary of the main results. So the main results is that the pinning defects are conformal, and they have this factorizing property in the infrared. And furthermore, the factorization channels are constrained by symmetry. And together with dynamical constraints coming from RG monotone, and also from symmetries, and also from the factorization property, we can often find solutions in the infrared, exact solution in infrared for such a RG flow, which is rare to come by for RG flows in the bulk. And this uses several ingredients from field theory, from general symmetries, and also from functional analysis. And at the end of the day, we have a very concrete prediction for what the infrared of such a flow look like. And in the paper, we give infinite classes of examples of such pinning flows in two-dimensional minimum models that populate a large zoo of possible fixed points that describe conformal defects in these theories, as well as in the ONCFT, three-dimensional ONCFT, and in the upcoming work, also in the Grosnevu-Yukawa CFT. And you may ask, how is this possible since RG in the bulk is so complicated? This is because we can make use of the knowledge of the full bulk CFT spectrum. So in all these cases, we have a lot of knowledge about the bulk CFT spectrum here from the fact that they're rational, and here coming from the bootstrap. And as we'll see that this together with this this symmetry and dynamical constraint will allow us to pin down what is the IR behavior of such pinning flows. Any questions so far?
Hi, Yifan. Can you hear me?
Yes. Yes.
Can you explain more detail about this symmetry enforced degeneracy? It matters, or it doesn't matter whether there's an anomaly?
So if there's anomalies, then the degeneracy will be forced. If there's an anomaly, then the degeneracy is a possibility, but there is also the possibility that there's no symmetry degeneracy, as we'll see examples.
Okay, thank you.
Yeah. Thanks for the question. So let's come to the examples. The first set of examples are going to be in two dimensions. The first example is perhaps in the simplest CFT known to us. That's the Ising CFT. And it can be described as a two-dimensional quantum field theory involving a single scalar field with a quartic potential and tuned to criticality. And this CFT has a very simple operator spectrum. There are three Virasoro primary operators. And out of these operators, only one operator, scalar operator, has dimension smaller than 1. And that's the spin operator sigma, has dimension 1/8. And so that could play the role of this operator O, the curly O, that represents that generate the pinning flow. And because there's no symmetry preserved by this operator sigma, all the Z2 symmetries is the symmetries in this theory are this Z2 symmetry and also the Kramers-Wenne duality. And both of those symmetries are broken by this operator. So we expect there's a single factorization channel for the infrared behavior of this pinning flow in terms of factorizing to boundary condition of the CFT. So to describe the factorizations, we also need to know what are the boundary conditions for the theory. And again, that's classified by Cardy. And we know the boundary conditions are either of the Dirichlet type, so plus minus, correspond to fixed spins to be either plus or minus in a lattice perspective on the boundary, or the free boundary condition. And their G functions are well known, so it's going to be 1 over square root 2 for these two cases. And for the free boundary condition, G function is 1. And these G functions are going to be important to decide which factorization channels are possible for such a flow as a consequence of the G theorem, because the G in the UV is 1 has to decrease on this pinning flow. And this is what I just said. So taking account the G theorem and taking into account also the fact that this flow is preserving the orientation reversal symmetry, the only possibility are these two. So you could either factorize into plus plus or minus minus. You cannot factorize into things like FF. That is because that G function is going to be equal to 1 as inconsistent with the G theorem. And you cannot factorize into plus minus because that one is not orientation reversal invariant, but the flow is orientation reversal invariant. You can fix that, of course, by adding the minus plus factorization channel, but then the total G function, again, will become equal to 1, and again, in violation of the G theorem. So that's how you can figure out these are only two possibilities. And these two possibilities are also realized by the spinning flow depending on the sign of the spinning deformation. So either for plus sign or minus sign, then you get these two possibilities. And furthermore, even though this flow breaks the symmetry, for example, breaks the Z2 symmetry generated by the topological defect eta, you can use the fusion structure of this Z2 symmetry defect eta with this interface to deduce the relation between these two flows. Namely, this deformation can always be the sign of deformation can always be flipped after conjugation with the Z2 symmetry defect represented by the left-hand side. But also, we know that this topological defect fused onto this derivation boundary condition plus will give you the derivation boundary condition minus and vice versa. So consistency, as represented in this picture, implies the infrared of the pinning flow given by plus H and minus H has to be related by conjugation with the eta topological defect. And thus, this again passes this check using the bulk symmetry, even in this case where the symmetry is broken. Okay, and this is the general way in which the symmetry, when it's broken, still leads to constraint among the possible IR outcome of the pinning flows. Okay, so maybe the pinning flow as a flow on codimension 1 slice is still a little bit counterintuitive. So let me try to connect, in the context of this example, connect the pinning flow to something that's more familiar, namely a flow in the bulk. And this is through connecting pinning flow into to something on the strip, as opposed to on the one-dimensional line, but on the strip. So suppose this is the kind of dynamical process we want to understand, namely the flow triggered by operator phi integrated on the line. We can think about how this is related to a flow on the strip triggered by the same operator. And these two pictures can be related by zooming out in the transverse direction. So in the cases where the operator phi has satisfied certain assumptions, when you zoom out, as far as observables in the separated in the transverse direction are concerned, this gives rise to the same IR behavior for such observables. But then in this picture, one can now understand the deformation using what we know about bulk RG. And in the cases where the operator phi, when you turn it on, gaps the bulk, then in this picture, in the middle region, we just get a TQFT. And then that leads to also boundary conditions for the left-hand side and right-hand side. So the picture in the bottom becomes a factorized space-time where you have boundary condition B nu imposed for the left and also imposed for the right. And suppose that if this diagrams commute, and this gives rise to a way to see intuitively how the infrared behavior of this pinning flow leads to factorization. And the possible degeneracy in the factoring channels through these pictures is also connected to the degeneracy that arises from the bulk RG flow. And as we know, the degeneracies of vacuum in the bulk RG flow are closely tied to symmetry. And this is one way to understand how symmetries constrains the degeneracy in fracturing channels for pinning flows. Any questions on this intuitive picture? Okay, so with this intuitive picture in mind, now we can look at one more interesting example in 2 dimension, namely the tricriticizing model. So we'll upgrade from the case where we have a quartic potential, but now to a sextic potential, again, to criticality. In this context, the operator spectrum is more interesting. We have 6 primary operators with respect to Virasoro, and there's also interesting symmetry generated by the Ising category and also the Fibonacci category that you probably heard about throughout this conference. And in this case, yeah, question.
Can I ask, so I think I asked you this question in another talk, but there was very little time.
Yeah.
You can expand a bit. So about the intuitive
Yeah.
picture. So strictly speaking, I think maybe you can pull up the picture. Yeah, perfect. Thank you. So the picture on the right is valid for conditions in which I take say operators in T and T on the left and on the right, and I send them very much further away than the scale of the orange in the the bottom picture the bulk coupling approaches the fixed point when I consider rescaling the whole system, and so when the orange slice is becoming very large. So
that's right.
It doesn't look like the two pictures commute. So I understand this is not your proof, but should we really believe this intuitive picture? In which sense?
Oh, so yeah, so you are completely correct. So there are three scales that's going on here. So there's a scale that characterizes the observable you are looking at. So like how far it's separated in the transverse direction. And there's a scale associated with the size of the strip. And then you have the scale associated with the dimensional coupling. So the scale we're taking, the limit we're taking is that we take the transverse, the scale associated with the observable to be very large in distance compared to the size of the strip. And furthermore, we take the size of the strip to be very large compared to the dimensional scale coming from the coupling. And it's in these cases where it's sensible to, I mean, it's reasonable to expect this picture to commute.
Okay.
Yeah. Yeah, thanks for the question. All right, so going back to the triangular icing example, and this is also the context where we'll address one of the previous questions, I think by Yang, is that in this case we have a richer family of flows which are triggered by these three operators: the energy operator, the leading spin operator, and the subleading spin operator. And these operators all have dimensions smaller than 1, so we can consider flow triggered by them. And furthermore, we also need to know what are the candidate boundary conditions where the factorization channel can be factorized into. And the 6 boundary states are labeled as follows. And this is using this, again, this lattice model motivated notation, this Bloom-Capell type lattice model, where per side you have 3 degrees freedom labeled by plus minus 0. And this plus minus 0 are analog of those kind of boundary Dirichlet boundary condition we had in the icing case. And D is like the totally free boundary condition or totally Norman boundary condition. And 0 minus and plus 0 are like mixed Dirichlet Norman boundary conditions. And to use the symmetry properties to deduce generalities in the factorization channel, we also need to know how these guys are related by the bulk symmetries. And in this case, here I just showed some arrows that tell us how fusion of the topological defects with the boundary conditions permute among the zoo of boundary conditions. Okay, for example, if you fuse the Z2 symmetry generator eta on plus, you get to minus. If you fuse the duality defect, the chromostranded duality defect on plus, you get to this 0 type boundary conditions. And then if you further fuse with the Fibonacci type topological defect, you get to the totally free boundary condition. Okay, and this D is the boundary condition with the maximal G function. All right, and because of the intuitive picture, we would expect a kind of a correlation between the bulk degeneracies under RG triggered by these operators to the defect factorization channels. So let's summarize what we know about bulk RG under these operators. First of all, the symmetry preserved by this epsilon deformation is just the V2 global symmetry. And the sigma deformation, as the case of the icing in the icing case, preserve no symmetry. Sigma prime, on the other hand, preserve this interesting Phipps symmetry. And this is the case where the symmetry has a non-trivial anomaly. The Z2 does not have anomaly. And of course, that's also evident from the phase diagram in the bulk, where the Z2 symmetry dependent sign, you could either have trivially gapped phase or you could have a symmetry breaking. But for this interesting case, we have anomalous symmetry. You are forced to have degeneracies in the ground states for either sign. Okay, and this is the case that's related to Yang's question. As you'll see, this is the case where you are forced, no matter what sign you take for the deformation, you are going to be forced to have degeneracies in the factorization channels. So this is the question that we're asking, and using the kind of general constraints from factorization together with G theorem and symmetries, which we briefly discussed. This leads to the following proposals for the infrared factorization channels for such pinning lines. And for the, let me just emphasize in the case of the sigma prime deformation integrated on a line, because the Phipps symmetry is preserved, we have this interesting kind of symmetry force degeneracies in the factorization channels that mimic what happens for the bulk RG. And these are, again, these possibilities, in principle, because you have 6 boundary conditions, there are so many factorization channels you can write down. It's from this basic kind of ingredients that rule out all the other possibilities down to the following entries in this table. And there are also numerical evidence from another Roy that confirm some of these entries. And I should also emphasize for those of you who like to study phase transitions, these are examples of something that we don't expect in one dimension for one-dimensional, like quantum mechanics or one-dimensional StatCat models. It's the notion of the persistent order. This is of course possible because we're looking at a one-dimensional, not kind of non-local one-dimensional system, because it's a one-dimensional system that's embedded in the two-dimensional gapless bulk. Any questions on this point? All right. If not, let's move on to more interesting examples, namely pinning flows in generalized pinning flows in 3 dimensions. Because we're studying codimension 1 flows, this will lead to interesting surface operator in 3 dimensions. We'll study these flows in garden variety CFT in 3 dimensions, and the common 3-dimensional CFTs are either the ON bosonic critical model or the Gross-Neveu model. So let's first talk about the ON bosonic model. It has this very simple Lagrange description. And in this context, a very nice pinning flow to consider is this localized mass deformation triggered by the ON invariant bilinear in the fundamental scalar. And this can be thought of as a localized mass deformation, has been studied since the 70s, and it was recently revived in this sequence of papers because there's interesting phase structure depending on the sign of this coupling. One could, at the zeroth order, one could ask whether this flow actually leads to non-trivial fixed points, and that's related to the question whether this operator, because of the non-trivial interaction in the bulk, actually has dimension 2. Has dimension smaller than 2 or bigger than 2. And from Bootstrap and also from larger analysis, there's strong evidence that for any values of n, this operator is actually relevant on the surface, has dimensions smaller than 2, and it's a leading ON singlet operator has this property. And in the bulk, this operator, the deformation by this operator, of course, is famous for understanding just basic phase transitions. And in the cases where the operator is turned on with positive dimension, the system goes to a trivially gapped phase. And if you turn on this operator with a negative coupling, the theory goes to the goes to the symmetry breaking phase with goldstones for n bigger than 1. And let's first focus on the case where the pinning field is turned on the surface with a plus sign. In this case, because in the bulk we have a trivially gapped phase, going back to the intuitive picture we presented before, uplifted to 2 + 1 dimension, we have this very natural conjecture that in the infrared, the behavior of the interface described by this factorization into what's known as ordinary boundary conditions for the ON 3-dimensional CFT. And this boundary condition should be thought of as the conformal boundary condition that descends from the Dirichlet boundary condition that sets all the scalar field equal to 0 on the boundary. And this is claimed to be the stable ON invariant boundary condition for the ON CFT. And this is supported by, and it was actually conjectured in this paper, by larger analysis. And in more recent works with my student and with Zemo, we provide further evidence for this IR factorization by doing calculation at finite n and using epsilon expansion. And then because for this proposal to work, there had to be a non-trivial matching between anomalous dimension of operators at the surface versus anomalous dimension of the operators at the boundary. So namely, so by phi hat, I mean the delta phi hat, I mean the anomalous dimension of the fundamental scalar at the surface calculated from this definition. I look for the fixed point in H. And for delta phi hat boundary, I mean the anomalous dimension calculated for directly by looking at the boundary ON invariant boundary condition, so-called ordinary universality class for the ON CFT. And for this proposal to work, these two numbers have to agree. And indeed, we found strong evidence for this agreement by comparison with numerical results at finite n from fuzzy sphere and from Monte Carlo. And one can also ask what happens with the pinning flow if you turn on the pinning field with a negative sign. In this case, it's conjectured and studied in this paper with the various evidences provided is that in this case leads to this very interesting extraordinary log surface universality. And from our consideration, together with factorization property, it leads to the following natural conjecture, namely in the infrared, the defect is described as certain factorized product of boundary conditions, factorized into boundary conditions, the so-called normal boundary conditions for low-end CFT, but smeared with the zero modes of the ghostones that come from breaking the ON symmetry to ON -1. And this again agrees with the results from these papers. And you can also ask what about pinning flows with other operators, for example, breaking the ON symmetry. And again, there's natural predictions coming from the constraints that we have. For example, if you consider the deformation given by just the fundamental field allowing a particular direction in the ON in the internal ON directions, it will naturally lead to just factorization into a single normal boundary condition. Okay, so let's now talk about the more interesting case, namely pinning flows in three-dimensional Grosvenor Yukawa CFT. This case is more interesting. So first of all, the Grosvenor Yukawa CFT at the level of Lagrangian can be realized by n fermions, Mariana fermions in this context, coupled to one pseudo-scalar and tuned to criticality. In this case, there's actually a three-dimensional family of pinning flows one can consider that are non-trivial. Namely, that could potentially lead to non-trivial conformal interfaces in infrared. This is because this operator pseudo-scalar phi is very relevant in 3 dimensions. And I should also mention that system has interesting interplay between the symmetry ON together with the space-time parity, and this will play a role in the subsequent analysis. And here I just list the properties associated with the pinning operators that we can infer from bootstrap analysis in these works, as well as larger analysis. So this phi operator, as I claim, is very relevant, has dimension much smaller than 1, well, significantly smaller than 1. And so phi and d phi hat are very relevant, and there's evidence that this seems to be relevant for all values of n on the surface. And phi square instead has operator that varies with n, and there's a crossover somewhere around n equal to 8 where the dimension grows beyond 2. And as is clear from large n, the dimension of this operator is bigger than 2. So this, from the IR perspective, this family of deformations, at least for n small enough, leads to non-trivial conformal defects in the IR, and for n bigger enough, could describe non-trivial UV fixed points of conformal interfaces. In the work to appear, we give a complete proposal for the 3-dimensional phase diagram of this family of RG flows, and we give with some assumption of minimality. We have the proposal charts all the possible fixed points that arise from this 3-dimensional space of flows. And to put the flows to put this chart somewhere, let's focus on the 2-dimensional subspace where this coupling constant H odd is 0. And because we're dealing with a garden variety CFT, and I thought it would be nice to put in the garden, so you can think about the garden as a collection of various defects in the Grosvenor CFT. And here we focus on this nice structure, which is a place to look for example, ON invariant conformal interfaces. And this blue dot represents the UV of this pinning flows, which amounts to having nothing inserted. And we have these flows coming down that's triggered by these pinning operators. And they could potentially end up with non-trivial fixed points represented by these colored dots. Okay, and there's a recipe to understand what are the possible fixed points. Again, we focus on the case where the coupling that's odd on the parity is turned off. The recipe coming from using factorization channel. So we'll be using knowledge on ON invariant boundary conditions, and also together with the monotonicity, namely that constrains the possible factorization channels, knowing the B anomaly for the boundary conditions, and also from the possible symmetry anomalies, and also directly from direct calculations when we can, say from large n and epsilon expansion. And this will allow us to fill in the dots. And of course, the dots will have to be compatible with one another, actually due to topological properties of just RG flows, as we'll see shortly. So at this point, we need to say something about boundary conditions of the 3-dimensional Grosvenor CFT that has been studied previously, which will, of course, be crucial to characterize the factorization behavior of these interfaces. The boundary conditions with ON symmetry at the Lagrangian level are realized by the following boundary condition of the fermions, okay, at the transverse location equal to 0. And interestingly, the parity anomaly, which is mixed with ON symmetry, forbids parity preserving boundary conditions in this ON invariant Grosvenor CFT. And this already have a consequence, as you'll see. This will force parity. This will lead to parity enforced degeneracies in the factorization channels under this pinning RG. And furthermore, boundary gravitational anomalies lead to further constraints on the boundary RG because the boundary RG should preserve the boundary gravitational anomaly because it does not break any of the translation and the Lorentz symmetries. And this is the kind of phase diagram for conformal boundaries of the Grosvenor Yukawa CFT that's proposed in this paper. And the B2 prime should be thought of as with this boundary condition, but on top of that, imposing a Norman boundary condition for the pseudo-scalar. B2 is imposing a Norman Dirichlet boundary condition for the scalar. And B1 is more exotic. It amounts to imposing a NAM-type boundary condition on the pseudo-scalar phi, or just allow a singular profile for phi. It's kind of a disorder type boundary condition. And they're also named as normal versus ordinary and special boundary conditions for the Grosvenor-Yukawa CFT. And the B anomalies for this theory also calculated. For example, at large n, they take these following values. And as you can see, they're consistent with RG flows. And in these two cases, you can also study the subleading contribution at order 1. And it's again consistent with the boundary RG. But one thing you should realize that this plot is certainly not complete because there are two things that are missing. For example, there are possible deformations coming from the normal derivative of phi turning on the boundary, which is not explored in its works. And second of all, the phi hat square operator, which trigger the flow from B2 prime to B2, can be turned on with either sign. It's unlikely that both signs give rise to the same boundary condition from what we saw in the ON model case. So both these kind of flaws need to be addressed to complete the boundary, the phase diagram of boundary condition for the Grosvenor-Yukawa CFT with ON symmetry. And as you'll see, there will be evidence coming from actually starting interface flow that the missing puzzle is given by this extraordinary type boundary universality for the Grosvenor-Yukawa CFT, where in addition to having this normal type boundary, very similar to ON case, there are emergent chiral fermions on the boundary. Just like in the ON case, there are emergent pseudo goldstones on the boundaries. Okay? And this is what's going to arise under this deformation, and under the phi hat square deformation with minus sign, a very similar kind of boundary condition shows up. But I do not discuss this just for the brevity. And what I checked again, it's consistent with the B theorem because the single Mariana fermion contribute in our normalization factor of 1/4, and this is consistent with the B theorem. Okay, so let me talk about the results. The results is that we're gonna actually kind of chart the entire phase diagram here, focus on the two-dimensional subspace. So we have answers to all the fixed points, namely the possible factorization channel into the boundary condition we listed before. And as I mentioned, because of the absence of a parity preserving boundary condition, the degeneracies is present in all the channels, except for these cases where something more exotic things happen due to emergent chiral fermions, emergent degree freedom, then topological degree freedom on the location of interface. And furthermore, we can give analytic supporting evidence for these flows, in particular the flow that leads to the dark red spots and the one lead to the pink spots from large n and epsilon expansion. This is made possible by separate studies in the case of interface versus on the boundary and compare them. And furthermore, these green spots can be inferred just by the topology of RG flows. For example, just to give you an idea, so for focusing on the region, for example, around these two fixed points, where you have the red fixed point and this dark red fixed point, which we know to be described by this factorization channel, and the knowledge that these fixed points are completely stable, so they give rise to sinks for RGs, and the fact that the other sides, namely from here and from here, are trivial, so they are described by sources. And just by arguments, basic arguments from topology of RG, as we explained more recently in this paper in systematically, it's a version of essentially the Poincare-Hopf index theorem. From the topology of the vector fields in nearby, you can infer there has to be at least one fixed point inside. And then again, together with constraints from G theorem, you can infer the only possible factorized interface that arises in the middle has to be this particular factorization. And for this to be consistent with the nearby RG flows, this predicts RG from this boundary condition B2 prime into the boundary condition B1 bar dressed with chi, dressed with this emergent chiral fermions. And this is how we give rise to, this is how we obtain further support for the thing I claimed before, namely there's this new extraordinary boundary universality. One can also understand this emergent chiral fermion from a different way, from anomaly matching coupling space. This uses this intuitive picture I presented before, starting from this picture where we want to understand RG flow triggered by this this derivative of the operator phi on the interface. This can be understood by blowing up this this interface into a strip, where interstrip will turn a bulk RG. But in this case, interestingly, we can consider the case where the bulk RG, the bulk coupling constant actually have a non-trivial spatial profile that depends on the transverse direction. So suppose the transverse direction labeled by X perp, and we consider this mass deformation in the bulk, which depend on this transverse direction and has this kind of step function type profile. And this is such that if we go back to, if we zoom out, this is such that it picks out precisely the normal derivative of phi in the interface limit. And if we go back to this picture and follow the bulk RG, we know the mass deformation will gap out the bulk, except at the point where the mass crosses zero. And from the arguments from anomaly inflow, and more recently phrased in terms of anomaly in coupling space due to this non-trivial profile of M, which should be thought of as a non-trivial background for the -1 form symmetry, together with this kind of anomaly theory in one higher dimension, it predicts the emergence of chiral fermions localized at location where the mass across zero. And because the mass gap theory on the left-hand side and right-hand side, it gave us the boundary condition, the B1 and B1, precisely those types inferred by the boundary, this boundary phase diagram that we talked about before. And together with the assumed commutativity of this diagram, this gives another way to infer the presence of emergent chiral fermions under this flow. Okay? So you can think about this spinning interface in the presence of this deformation derivative of phi as a way to engineer to factorize to produce a factory for 2D chiral fermions from nothing. And here just a summary. So we in this talk we discussed generalized spinning flows as a version of RG flows generalized to higher codimensions, and we saw this very remarkable property that the spinning flow factorizes spacetime into two halves, where the infrared behavior interface are described in terms of boundary conditions, and these factorization channels are further constrained heavily by RG monotonicity theorems, symmetries, and also their anomalies. And this allows us to give precise predictions for how the interface behaves in the infrared. And furthermore, in some cases, in the case where the continuous symmetry is preserved by the flow, there are interesting emergent gapless degrees freedom, for example, gapless goldstones and also gapless chiral modes that arises from nothing. And there's a number of speculations, and here, because I'm running out of time, let me just flash them and mention that one observation is that the pinning flows that we study, they always seem to end up with stable fixed points, namely that at the fixed point of these pinning flows, if you study the possible operators on the interface, and if you insist on the symmetry preserved by the flow, you see that all those operators will be relevant on the at the codimension 1. So they provide examples of what's known as self-organized criticalities for defect RGs. And it'll be interesting to study whether the G functions of this spinning defects therefore provide possible symmetry enriched versions of G theorem that's namely a stronger lower bound than just G greater or equal to 0 from unitarity. And there are also many applications. For example, it'll be interesting to study the spinning defects in lattice and also in gauge theories. And in those cases, it'll be interesting to understand under dualities that applies to the lattice model and gauge theories, for example, three-dimensional bosonization dualities, how the spinning defects are related to one another. And furthermore, it'll be interesting to understand the holographic dual of the spinning defects, which in which case non-trivial geometries should arise. And there are also generalization of the pinning defects I discussed over here by considering instead of starting from a trivial defect, but a more non-trivial topological defect or a direct sum of topological defects. And also by considering instead of local operators, you can consider slightly non-local operators turned down in the UV, for example, by two-step operator, as explored in the recent papers. And furthermore, one can consider even more general scenarios where the pinning flow is not on the line, but directly on the strip. And you consider the case where the flow does not necessarily gap the bulk in the strip. And in which case, to understand the interface that arises in the infrared from a large transfer separation, it would amount to understanding fusion of the corresponding RG interfaces. All right, that's all I want to tell you, and thank you for your attention.
Any questions? Yes.
I wanted to know how you deal with the case of two decoupled CFTs, like two free scalars, and you gap.
Yeah. So right. So very good. So in the factorization statement, we assume there's a unique stress tensor. So of course, if you have decoupled theories, the factorization is going to be about factorization for a particular stress tensor. So the decoupled factor would not. I mean, if you are turning on the operator which only coupled to one stress tensor, the other sector is not going to be factorized. So there's energy transmission, of course, for the stress tensor, which does not talk to the pinning field that you turn on.
Other questions? I maybe have one question. You mentioned pinning defects on the lattice. How should I think?
Yeah.
Is it just you take some spin? Let's say I'm in 1+1 dimension.
Yeah.
Take some spin.
Yeah.
I do like a local impurity, and then I
Yeah, very good. Yeah, so actually, so this is, I found out about this while preparing for the talk. There was a paper actually, I'm sorry, I forgot the authors that studied on the lattice. So the particular context they were studying is the case of the Lehlinger liquid, and it's precisely what you said. You consider a localized impurity on the spin chain. And then you consider you consider its critical behavior in infrared. You study, for example, correlation functions of spins away from the impurity, and you will see its behavior is gonna essentially this spin chain is going to be cut in halves as far as observables are concerned. They measure, for example, correlations of spin spin operators across the interface.
I see. Thanks.
So it is cutting the spin chain. So
yeah.
I mean that, yeah.
Any final questions?
But of course, you have to go to sufficient system size. So that's the I think for numerical simulation, that's the hard part. Yeah.
Okay. Any final questions? If not, let's thank Yifan again.